We will be discussing how to name ionic compounds, sometimes referred to as nomenclature. It will be useful if you have a periodic table in front of you. The names for monoatomic cations are relatively straightforward, and identifying the charges is likewise, for most cases, relatively easy. If you're dealing with main group elements, the cations that are formed generally correspond to the group number. So, for example, elements in group 1 tend to form 1 plus ions as their only ion. Elements in group 2 form 2 plus ions. If you go over into the P block, group 3A, elements that are lower down in the periodic table tend to form positively charged ions with a 3 plus ion, but also can have positive ions that have 2 units of positive charge less. So, for example, thallium can form both a 3 plus and a 1 plus ion. If we go over here to tin can form a 4 plus ion and a 2 plus ion. Those differences in 2 charges corresponds to the 2 electrons in the s-type orbitals. For the transition metals, it's a little more complicated. These are have possibly multiple positive charges. Oftentimes these elements have a 2 plus ion, but can also have 3 plus and higher positive charge ions as well. These generally are things that you will gain knowledge about as you work through this course. Finally, if we're dealing with the non-metal elements in the main group, which are up in the top right-hand corner of the periodic table, these tend to form negatively charged ions, where the charge corresponds to the group number -8. In other words, they gain enough electrons to have a closed valence shell, and this then produces the same number of valence electrons as the noble gases. To name the monoatomic cations, we first would use the name of the element and then simply add the word ion. So, for example, a lithium, which is +1, would be called a lithium ion, since there's only one possible charge. For elements that are in the D block, or the transition metals, since they have more than one possible positive charge, we have to somehow differentiate between the various positively charged ions. To do that, we add a Roman numeral after the element's name. This Roman numeral will correspond to the charge of the ion. So, for example, if we have vanadium, which is 5 plus, this would be named the vanadium Roman numeral 5 ion, whereas a vanadium, which is 4 plus, would be vanadium Roman numeral IV, or Roman numeral 4, and then ion. So for the monoatomic anions, the negatively charged ions of the nonmetals, we again use the name of the element involved. We use the root of that element's name, and then we replace the suffix with the ending "ide." And so, for example, sulfur with a 2 minus charge would be sulfide. Oxygen with a 2 minus charge would be oxide. Fluorine with a 1 minus charge would be fluoride, and so on and so forth. In general, we will be using the most recently developed naming system by the International Union of Pure and Applied Chemists, the IUPAC system, but there are older systems which you should be at least sort of familiar with. The naming of the monoatomic cations oftentimes would involve using suffixes of us or ik. This simply indicates whether we're dealing with a lower versus a higher oxidation number, and those are added as suffixes. So for example, iron has two very common ions, like 2+ ion and a 3+ ion. The us is the 2+ ion, the ic is the 3+ ion. This slide compares the newer International Union of Pure and Applied Chemists system using the Roman numerals to the older naming system with the suffixes. So some examples are things like chromium, which is 3+, chromium Roman numeral 3 compared to chromic ion. And then we might have something like cobalt, which is 2+, so cobalt Roman numeral 2 versus cobaltous ion. There is a cobaltic ion as well. So again, we are going to focus mostly on the more newer and more systematic system. In addition to the monoatomic ions, there are a number of polyatomic ions. These are groups of atoms that end up having positive or negative charges, and you will need to memorize these formulas and corresponding charges. Shown here is a table of the polyatomic ions that must be memorized. You should memorize the name and the corresponding formula along with the charges. This is not an optional exercise. And in many cases, there is some method to the madness associated with naming these polyatomic ions, and so if we can get used to some of the suffixes and prefixes in the system, it makes it a little bit easier. So, for example, there are two of the oxyanions of sulfur. In the first case, there are 3 oxygens and a 2- charge, whereas in the second example, there are 4 oxygens and a 2- charge. The suffix for the anion that has a 3 oxygens is ite, so that is the sulfite ion, whereas sulfate has 1 more oxygen than the sulfite. So, basically the rules state that ite is always going to have 1 fewer oxygens than 8. It turns out that there is sort of a pattern to this, in that if the element that is the first element in the polyatomic ion is in the second period main group, that's things like carbon, nitrogen, then the maximum number of oxygens will be 3. Those will be the 8 ions. If there is 1 less oxygen, that would be ite. Whereas if the element is in the third period of the main group, then the maximum number of oxygens will be 4. Those will be the 8, and 1 less, in this case 3, would be ite. In some cases, we have more than just 2 oxyanions, and that then requires the use of prefixes in addition to the suffixes. Good example of this are the chloroxyanions, and so in this case there are 4 of them. The one with the maximum number of oxygens, which is 4, is going to have an ending of 8, but to differentiate that from the one that has 3, we use a prefix, and the prefix is per. So there are 2 oxyanions of chlorine that have an ending of 8. The chlorate is got a formula of ClO3 and a -1 charge, whereas perchlorate has 1 additional electron per, meaning the most. You'll notice in all of these oxyanions, the only thing that is changing is the number of oxygens. The charge is always the same. On the other end, there are 2 ite ions. The ite ions, again, differ by the number of oxygens. So chlorite has one fewer oxygen than chlorate, whereas then to differentiate the ClO minus, this is given the prefix of hypo, which is the lowest or underneath, and so the hypochlorite ion has one less oxygen than the chlorite ion. So knowing those prefixes and suffixes are useful. It turns out there's a whole series of ions in which we can replace an oxygen with a sulfur, and in this case the naming system is such that we would add the prefix thio. Thio means that there is sulfur in the formula. And so in this case, we compare the formula of sulfate, which has one sulfur and 4 oxygens with a 2- charge. If we replace one of those oxygens with an additional sulfur so that there ends up being 2, we would refer to this as thiosulfate. Cyanide, likewise, we can compare that to adding an oxygen, and in this particular case, we go from forming the cyanide ion. Ide usually means a monoatomic anion, but in this case, there are actually 2 atoms in the formula. But then we go and add an oxygen to it, and we use the suffix -ate to differentiate it. And then finally, if we replace one of that oxygen in cyanate with a sulfur, this would be thiocyanate. So as an example of how to go about naming an ionic compound, if we're asked what is the name of VCl3, in this case we would need to know that it is an ionic compound. It's comprised of a metal and nonmetals in this case. It then will not be a polyatomic ion because its formula doesn't contain a grouping of atoms that is the same as the list of polyatomic ions that you have memorized. So in this case, the first element will be the positive ion. That's the vanadium. The vanadium can have more than one oxidation number, so the challenge then becomes, what is the positive charge of the vanadium? Well, to figure that out, we have to then know that the chlorine is going to be a 1- ion, and that is because it's a main group element and it needs one additional electron to be like a noble gas. And therefore, if there are 3 of the chloride ions, each chloride being 1-, then there has to be a corresponding amount of positive charge from the vanadium, so there has to be a 3+ charge on the vanadium. So hence we name the cation first using the Roman numerals. So this is vanadium Roman numeral 3, and then we name the anion, chloride. In some cases, you will need to include waters of hydration in the formula, and in this case you'll need to know some prefixes that tell us the number of water molecules. These are Greek prefixes that are very familiar to most of you, so things like mono, di, tri, tetra, so on and so forth. Turns out that cobalt 2 chloride forms a hexahydrate quite readily, and there are many other transition metals that form hydrates as well.